audio. Okay, so if we have two events, E and F, they're independent if the probability of E given F is just the probability of E. So F has no impact.
Sure.
Yes.
I don't blow
If E and F are not independent, then they are said to be dependent. So here it's one or the other. You're either independent or dependent. So if it's not independent, then they must be dependent. Now, that's not to say we're going to see that relationship, but if you're not independent, then you must be dependent. That's what it boils down to.
If you draw a king and then 12 other cards that are not a king, it would still be the same probability of drawing a king next time, right? That wouldn't affect your probability of drawing a king.
What do you?
Because the probability of drawing a king is that is 1/13.
Uh-huh.
If you draw a king and 12 other cards, it would still be 1/13.
If you drew 12 other cards,
Okay.
yes. But if we're just drawing like 4 cards, then yeah. Now, if the probability of E given F is the probability of E, we can also flip it around to say the probability of F given E is simply the probability of F. So sometimes the knowledge of that one event has occurred does not change the likelihood that another event occurs. That's like we talked about on the coin flip. Flipping heads the first time does not change the fact that there's still a 50-50 shot next time of getting heads or tails. So let's consider the genetic trait of a hitchhiker's thumb, which is the ability to bend the last joint in your thumb back at an angle of 60 degrees or more. So on my left hand, I can do it. My right hand, it's not having it.
Yep.
So we're just talking about the hitchhiker's thumb gene. So it's being able to bend your thumb back more than 60 degrees. Yeah. I can do it on my left, but not on my right. Okay, anyways. Whether or not an offspring has hitchhiker's thumb is determined by 2 random events. Which gene the father contributes, which gene the mother contributes. Now, the gene that the father contributes does not in any way, shape, or form change or affect the gene the mother contributes. So to be independent events. So let's look at a banking example. So suppose the bank offers both adjustable rate and fixed rate loans on single family dwellings, condominiums, and multifamily dwellings. The following table, which we call a joint probability table, displays probabilities based on the bank's long-run bank loaning process. So 40% of their loans are single-family adjustable. 21% of their loans are condos, adjustable, etc. not related to this problem, but what kind of loan do y'all think would be better? Adjustable interest rates or fixed interest rates?
Depends. Yeah, it depends on the current stage of the business.
True. Very true. Yeah. Depends on the stage of the business cycle, and then also, I feel like it also depends on the budget, your budget. If you need a hard amount, like my mortgage is going to be this amount every month, end of story, I can plan for that. Probably go with a fixed rate mortgage. Adjustable, you're at the mercy of the market. If it's just for like a mortgage. Rates go up, your rate goes up. Rates go down, your rates go down. So, anyways, back on topic. What would the probability be of getting an adjustable loan? How can I find that? Probability of being adjustable. We add up these three, and they get you 0.7. So the probability of an adjustable loan is 0.7. Now, let's look at the probability of an adjustable loan given that the loan is for a condo. So how can I set this one up? What goes on top? 0.21, good. 0.21 goes on top, what goes on bottom? 0.3. Remember, the second word goes on bottom. Second word goes, so it'd be 0.21 over 0.30. Which also gives you 0.70. So what do we notice? Did the fact that we're getting a condo impact our chances of getting an adjustable loan?
No.
No, it didn't. So we would say that these two are independent. Knowing that the loan is for a condo does not change the probability that it is an adjustable rate loan. Therefore, the event that a randomly selected loan is adjustable and the event that a randomly selected loan is for a condo are independent. Notice the specific wording of this statement though. We're only talking about adjustable and for condos. We're not saying the type of house is independent of the type of loan. We're just saying that getting a condo is independent from the probability of the type of rate.
Mr. Short,
Yes.
where did the 0.3 come from?
This 0.3,
Yes, sir.
that's the probability that the loans were from condos.
Oh, okay, I see it.
Yeah. Questions on this one? Okay. So now we're going to revisit that job satisfaction example that we did yesterday. So I went on and printed the table in your notes for you that we didn't have to look back at it. So they ask us, are being a college teacher and being satisfied with your job independent or dependent events. So let's apply what we just talked about to this example. Okay, so we need to look at first, what's the probability? I'm going to call this method 1, which, just so I have a title up here. Because we're going to learn about method 2 a little bit later. So are they independent or dependent? Well, let's see. What's the probability of being a college teacher? What does the table tell us?
0.1504.
0.1504. Okay, now I need to check the probability of being a college teacher given that they're satisfied. Is that calculated not coming on?
Yeah.
1951.
Oh, there it is. Okay, so what number goes on top here? 0.0951. What should go on bottom then? No. Yes.
Factor is 0.174495.
The 4 decimal places, what was it?
11745.
Good. Okay, are those the same? No. So what this tells me is that knowing they're satisfied changes the probability. So are these independent or dependent? They're dependent.
Yeah. Oh, dependent means change.
Yes.
Gotcha.
So since the probability of college is not equal to the probability of college given satisfied, C and S are dependent events.
Do you have a trick that or some type of thought that might maybe help us to remember how dependent is changing and independent no change? Now you're kind of confusing myself. If I was alright, I'll just check.
I really don't.
Alright, that's cool. I'll figure it out.
One thing I can think of is like related to texting. If you ask someone like where do you want to go and they say I don't care, what's the shorthand for I don't care?
Obviously.
Obviously, independent doesn't change.
Okay.
That just randomly popped in my head, but.
Thank you.
Uh-huh. Okay. Let me go back to the PowerPoint. So this is all stuff that we just did. Since they're not equal, they're dependent. Okay, so let's look at the multiplication rule for two independent events. So let's say we have two events, E and F. They are independent if and only if the probability that they both occur is equal to the product of their individual probabilities. The probability of E intersect F is equal to the probability of E times the probability of F. That's and, yep. Okay, so let's look back at the hitchhiker's thumb example. Suppose there's a 0.10 probability that a parent will pass along the hitchhiker's thumb gene to their offspring. What's the probability that a child will have a hitchhiker's thumb? Well, this will happen if the mother contributes a hitchhiker's thumb gene and if the father contributes the hitchhiker's thumb gene. So we would have to multiply them together. 0.01 for the mom times 0.01. Wait, sorry. You just give me 0.01 is the answer. I'm thinking 0.1, sorry. Yeah. So you're right. 0.1 times 0.1 gives you 0.01. Yeah. That's the probability. So this is yet another way to see if two items are independent or dependent.
Could you go back real quickly?
To
Where's P over H plus from mom and all that? All right, I'm good, thank you. I'm sorry, could you go back one more time? I didn't realize it was a blank right there.
Yep. The green box is a blank.
I'm just trying to get the equation. All right.
Okay, I think this example is a little outdated now, but let's go with it anyways. So now, I personally don't have a VCR, but my parents do. Yes. So a VCR is, I don't know if y'all remember like the tapes, like you'd watch movies on. They're like a, yeah. The VCR is the box that you put the tapes in to watch movies before DVDs came out. So let's consider the person who purchases from two different manufacturers, a TV and a VCR. Suppose we define the events A and B by A is the event that the TV doesn't work. B is the event that the VCR doesn't work. Suppose the probability of A is 0.01 and the probability of B is 0.02. What's the probability that the TV and the VCR do not work properly? Well, if we assume that events A and B are independent, then what could we do to find their probabilities? Yeah. So you would multiply 0.01 times 0.02. That's like the full equation in all of its glory.
PA intersect B equals 0.01 times pi by 2.
Yeah. Yeah, if you just want to write down PA intersect B equals, and then this part, that works. As long as you know what it, on the homework, I see what you're saying, because that's AP grading and stuff. But as far as notes go on this, as long as you know what you're writing down. Okay, questions on this one?
I can go up quickly.
Sure.
Thank you.
Okay. And then next. Okay, that works. There you go. Okay, so let's go back to our job satisfaction survey. So now we're going to look at another way to determine if C and S are independent or dependent. We already kind of know the answer, but let's do the second method now. Method number 2. Okay, so for this one, let's just go on and pull all the probabilities that we'll need to work with from the table. So what's the probability that they are a college teacher?
Yeah, 1504.
1504. What's the probability that they're satisfied? .5450. And what's the probability of being a college teacher and satisfied? 0.0951. Okay, so really we're kind of through with the table at this point. Now that we have all our values, so let's see. If they're independent, we should be able to multiply these two together to get that. Let's see if it happens. The probability of college times the probability of satisfied equals 1.1504 times 0.5450. Into 4 decimal places, what would that give us? .08. That'll be 20. That's right. I'll admit, even I have to think of those. I'm like, wait a minute, 19. It's like what? 196. The 6. Wait, the 9 goes to. Oh, 19 goes to 20. Oh, okay, I got it. No. I even have to think for a minute on that one. Okay, so moment of truth. Are these the same?
No.
These are different. So since, let's make a conclusion now. Since the probability of C times the probability of S is not equal to the probability of C intersect S, we can conclude C and S are dependent events. Yes. Yes. Okay, let's go back to the PowerPoint. So this red, where we said they're dependent events, that's actually a blank below the example. Because that C and S are dependent events. I don't know if y'all caught that. Did we catch that blank early at the bottom?
Dependent?
Yeah.
Sure.
Okay. So really, this is, if you're given a table, this is one of the more common ways to check for dependence. Because it's just easy. You can look and say, okay, 0.5450 times 1504. Oh, no, that doesn't give me that. So it's dependent. Next. I mean, it's just a real quick check. Okay. Now, that was for 2 events. We talked about the multiplication rule for 2 events. Now let's look at K events. So if we have events 1, 2, 3, all the way to K, and they're independent, if knowledge of some of the number of the events does not change the probabilities, then we just can multiply all probabilities together, and that gets you the probability that they all happen. But they have to all be independent of each other. If like 1 and 2, for instance, since those are the main 2 we can see up here. If 1 and 2 are dependent, even though the rest are independent, we use this. They all have to be independent of each other. Yes.
There's like 8 events, and one of them was independent and the rest was dependent. How would you find the probability?
So you would have to let me look that up and get back with you actually. Yeah. I'll have to look that one up and get back with you. Good question. Now, this relationship remains valid even if one or more of the events are replaced by their complement. So let's say we kept everything the same except we wanted the event that E1 does not occur. I could replace this with the complement and the relationship would still work. I could still multiply like this, even though one's a complement. Okay, so let's suppose we buy a desktop computer system. And it consists of a monitor, a mouse, a keyboard, the CPU, and extra storage devices. Most computer systems have problems due to manufacturer defects. Or you could be like me, have a computer that's 1 week old and open a virus. But then claim it was defective. My dad, I was helping my dad run his business, and he gets an email saying, attached is your invoice for your recent order. Remember, payments due within 30 days. And he had just ordered stuff. I'm like, oh, this must be the receipt or the invoice for it. I click it, and it was ransomware, meaning it encrypted my whole computer, all my files, and then just flashed a message on the screen. To unencrypt your files, please pay $500 to this person. Oh, did I seriously just fall for that? Dang. So I took it to Geek Squad and they were able to unlock everything. And then it started just it's never been the same since then. It's been messing up since day one. So it was under warranty. So I just like, this isn't working. Oh, send it in. It's under warranty. Okay. We put a new hard drive in there. It should work now. I get it back. Well, now the graphics aren't working. Oh, send it in. It's under warranty. Okay. It doesn't work. Now I can't even open Google Chrome. Like it'll crash the computer if I open Chrome. So I don't know what's going on. Anyways, so on this computer, let's let E1 be the event that a newly purchased monitor is not defective. E2 is the event that a newly purchased mouse is not defective. E3 is the event a newly purchased disk drive is not defective. And then E4 is the event that a newly purchased processor is not defective. So we're going to suppose that the four events are independent, where the probabilities of the first two are the same at 0.98. The probability of event 3 is 0.94, and the probability of event 4 is 0.99. So what's the probability that none of the events are defective? How could I find that? Multiply them all together. And you get, you're right, but what else you multiply? Because I only see three numbers up here. That's right. We have the same, we have 0.98 for two events, so I have to multiply by 0.98 twice. So 0.98 times 0.98 times 0.94 times 0.99.
Upside down Jews, I always make them look like N's by mistake.
Well, that's one way you can remember they mean intersection.
So,
In intersection.
yeah.
Okay. So in the long run, 89% of our systems will run properly when tested shortly after purchase. So that's how we would interpret that result. 89% of our systems will run properly when tested shortly after purchase. So now let's find a probability that all components work properly except the monitor. The monitor, they sold us a broken one. So if the probability that the monitor is not defective is 0.98, what's the probability that our monitor is defective? 0.02. So the probability that the monitor is defective is 0.02. The rest is just the same.
We're gonna have as much vocab as we did in the last section.
Hey, what?
We're gonna have as much vocab in the last section, like we did in the last section.
Yeah.
I thought you said that one was like more vocab.
Well, I mean, you're still gonna have to know vocab words and stuff.
That's true.
It is hot in here.
I don't know myself, that's hard.
It's what?
It's the best country classroom, been all day, all day.
I would rather
I need those classrooms.
I'd rather be in a freezing room than a hot room.
I'm too big for the heat.
No. I like the heat better. I'm not a fan of the cold.
Let's just show, I got one else, please.
I laugh at the saying. The thing with the cold, you can always bundle up to stay warm.
Yeah,
Your hands stop working.
yeah,
With
but
the heat,
school tends to frown on people who start stripping in class.
exactly. The heat, there's only so much you can take off before it starts being frowned upon. So, yeah. Okay, so if we calculate the probability that just the monitor does not work, we would have to do the complement of E1, so 0.02, but then everything else works fine. So 0.98 comes 0.94 comes 0.99. And you should get 0.0182. Questions on this example? Okay. Then let's look at sampling schemes. So sampling is with replacement. Once selected, an individual or object is put back into the population before the next selection. Sampling is without replacement if once selected, the individual or object is not returned to the population prior to selecting again. So let's look at a card example. Suppose we're going to select 3 cards from an ordinary deck. Let's consider the events. E1 is that the first card is the king. E2 is the event that the second card is the king. And then E3 is the event that the third card is the king. So we're going to look at this 2 different ways. We're going to look first with replacement, and then we're going to look at without replacement. And I'm actually going to work these in a slightly different way than what's up on the PowerPoint. I get it, notation is important, but I don't want to bog us down too much notation that we get confused about what's actually happening. Okay. So we're going to do with replacement first. So we want to find the probability that all three cards will be a king with replacement. How many kings are in a standard deck? 4. I'm just going to make note. There's 4 kings. How many total cards? 52 total. Now, how many are we wanting to draw? 3. So I'm going to do 3 blanks. First blank is the probability of E1 happening. Second blank is the probability of E2. Third blank is the probability of E3. Remember, each event is that we get a king. And here we're doing it with the replacement. So I'm going to go draw my first card. What's the probability I get a king? 4 out of 52. Or 1 out of 13. 4 out of 52. Okay, I'm going to replace it before I draw my second card. So what would my probability be on the second card? 4 out of 52. Again, I'm going to replace it before I draw again. So what would my probability be on the third one? 4 out of 52. So to get the probability that they're all 3 going to be a king, what will I need to do? Multiply them all together. This time I want our answer to 6 decimal places. .0000455.
Oh, this is why if you guess somewhere in the list, just go straight down one choice instead of changing choices. Yeah, I can see how it's better than changing choices.
Yep, it all deals with, it actually deals with what's called expected value, which we're going to get into in chapter 7. It's just the fact that, let's say there's 5 answer choices. If you pick different ones each time, you're essentially resetting your probability. But theoretically, if there's 5 answer choices on the 20-question test, 4 of those 20 would be the same answer choice. So if you just wanted to pick a letter, essentially say YOLO, and then just go all the way down, then theoretically you'd get a 20 on it. I did see a professor one time though, like he made, even for those that knew it, he kind of psyched them out because it was a 50-question test. All 50 answers were D.
I would have made it 51 question, not 8.
It's such an evil thing to do.
That really is.
Yeah. I never had the professor, but I saw him like, that's just cruel. That's just manipulating people's minds right there. Like you would have to be 100% sure you know what you're doing to make 100 on that test.
Or just YOLO.
Yeah. Got a 20% chance of making 100 here. Let's go.
I would have made it 50 question 8 or something.
Just so no one made 100. Unless they knew what they were doing.
Yeah.
And there'll be that one dude who really doesn't care and just like Put it all the way down.
Yeah. After about the 10th one, getting the same answer, like, I noticed something going on here.
See, that's my thing. After I get it like more than 5 times, the same answer, like I know
If I get it,
I know they do what
if
they
it
do.
goes 3 times in a row and I'm starting to think that this one might be the same one, I'd rather go back and check these answers.
Yeah, exactly. Yep.
I just go with the flow.
Go with the flow.
No, I'm like, alright, something's wrong here.
Yeah. Okay.
I'm almost there.
Let's look at it without replacement. So, again, we still have 4 kings, we still have 52 total, but this time, we're not replacing cards. So, still 4 kings, still 52 total, but no replacement this time. So, for the first event, what would be my probability of drawing the first king? 4 over 52. Okay, so I draw a card and woohoo! Luck is in my favor. I got a king. What's the probability of doing that again?
What if you drew it? Isn't there the, if you did draw a king, maybe 4 over 51. Or if you did draw one, maybe 3 over 51.
Yeah, we're gonna say draw one.
Okay.
We did draw. So we're gonna on these this type of example, we're gonna assume we get what we want. So what would the probability be for the second one? 3 out of 51.
Is it just E1 on
Is it what?
those? Is it just E1 on those and not D E1?
Well, it technically is.
Okay, I'll just make sure one of those.
I'm just being lazy. So what would be the probability of the third one? 2 out of 50. So the probability that we get a king on the first one, a king on the second, and a king on the third, we would just multiply all these together. And what would that get us? 0, 0, 0, 1, 8, 1. So it's actually more likely to do it if you replace it each time.
So what is the hypothetical for how you do it in this other one? Like you put the card back in the deck on the first one?
First one, you put the card back in the deck. Good on you. So we mean by with and without replacement.
So the chances get smaller?
Yeah.
Because you're limited, you know, kings in the next one. You're narrowing the window of probability.
Okay, any questions on this example?
Say, what if I got 3 kings in a row without replacement? I'd go buy the
Okay, so this is just same thing we just did. So I'm gonna bypass it. So on the top of page 18, so let's flip over. Suppose I'm going to pick 2 cards from the standard deck. This can be done 2 ways. First way is I pick a card at random, replace the card, and then pick a second card. What would that be? Independent or dependent?
Independent.
What is it?
So I can pick cards two ways. This first time, I'm going to pick a card, replace it, and then pick another.
But you would replace the second one?
Well, I'm just drawing two.
It'd be independent.
Is the independent?
I don't know, like, the second part got me confused.
The second one would be independent because you're narrowing how many cards you can choose, therefore restricting your amount.
Let's see. Since we're sampling with replacement, meaning we're putting the card back, these events are typically independent. We draw a card, we put it back in the deck, and then we draw another. Those are independent events. Now let's say we pick a card at random. We do not put it back in the deck before we draw our second one. These would be dependent because we did not place it back in there. Once it's out, it's out. So let's say I'm going to pick two cards from a deck without replacement. I'm not putting them back in. What is the probability that I'll select two spades? So that would be the probability for the first card, 13 over 2. I'm not going to put it back, so then what would be the probability for the second card? It's 13. Well, it's 13 out of 52 because there's 52 cards. 13. Hang on, I'll back up. Let me back up. Okay, let me screenshot this and then we'll work it together. Okay, so I'm going to draw two cards from a standard deck of cards. Okay, in a standard deck of cards, how many total cards are there? 52. So standard deck has 52 cards. How many spades are in a deck of cards? That's right, there's 4 suits, so 52 cards. You know what 52 cards divided by 4 suits gets you how many cards per suit? 13 cards per suit. Okay, so we want to get 2 spades. So I'm going to do 2 blanks right here. This first one's going to be spade number 1. Second blank's going to be spade number 2. What's the probability of drawing spade number 1? 13 out of 52. Now, I drew 1 spade out. How many spades would be left? 12. How many cards are left now? Okay. Multiply these together and they get you your probability of drawing 2 spades. 0.05. What were you saying? You say 88?
Yes.
Okay.
Does this make a little bit more sense now?
I had a different paper that didn't.
Yeah.
And so this is like, when you take one out and you don't put one back.
That's right. This is without replacement. Okay. So they left it as a fraction, 1/17. I mean, we don't have to, but we could. If we felt so inclined to do so. Okay, let's move on to the next one. So let's say we're trying to select a jury that contains, from a pool that contains 12,000 potential jurors. 3,000 of them are African American women. So let's say we have 4 events. Each event is basically saying that you're picking a African American woman to be on a jury. Now, let me ask you this. If you get picked to be on the jury, can they pick you again? Not for that same trial, right? They can pick you for another one, but for that certain trial, can you hold 2 seats? No. They're only going to let you hold 1 seat. So, we want to find the probability that all 4 are African American women.
Gotcha.
So clearly we're going to have to sample without replacement. There's no way we could do this where we put people back and pick them again. I'm just going to show our probabilities here. So the first time we pick, there will be the full 3,000 left. The 3,000 out of 12,000. That's the chance of an African American woman getting picked. Each time we're assuming one does get picked. So how could I find the probability that all of these occur? That all 4 occur. Multiply them all. That's right. I'll give y'all a second to multiply these out. And then we're going to ultimately round our answer to 6 decimal places.
How many decimal places?
6.
For me, the last two things.
There's a reason we're doing 6. Right now it may not make sense, but there's a reason we're doing 6. Alright, so what did y'all get when y'all multiply them all together? When you multiplied all of these together, what did you get? And like I said, you may be wondering, why do we need the 2 zeros at the end? We'll see why here in a second. Okay. Let's just suppose that we're going to replace them. But if we treat the events as being replaced, so we're going to do them independently, then what would the probability be for each one? 3,000 over 12,000. If we replace them, every time it would be 3,000 over 12,000, which is essentially 1/4. So now we're going to do the same process. We need to multiply 1/4 times 1/4 times 1/4 times 1/4. And when you do that, you should get 0.003906. Hopefully now you're starting to see why we rounded to 6 decimal places. Are these exactly the same? No. Oh, are they pretty darn close? Yeah. They're 6 millionths away from each other. That's it.
You still consider
Well, in this case, we assume they were independent. We're actually about to talk about what's going on though. That's what these bullet points at the bottom talk about. Okay, so notice that the result we calculated by sampling without replacement, what was 0.003900, and the result calculated by sampling with replacement was 0.003906. These results are substantially the same. There's not hardly any difference in these. That's that blank on that first bullet at the bottom, the same. So clearly, when the number of items is large and the number in the sample is small, the two methods give you essentially the same result. Because the number that we're pulling from our population is big, but our sample is small. So if a random sample of size n is taken from a population of size capital N, the theoretical probabilities of successive selections calculated on the basis of sampling with or without replacement differ by insignificant amounts under suitable circumstances. So you may be wondering, okay, so where's the cutoff? How do I know if I can assume they're independent? Well, if your sample size is less than 5% of your population, then we can assume independence. Under which one? Large and small. Questions? We're almost done. One more example. So let's suppose the manufacturer of a certain brand of light bulb made 10,000 light bulbs. 500 of them are defective. You're going to randomly pick a package of 2 light bulbs off the shelf. What's the probability that both light bulbs are defective? So they ask us this question, are the events, being E1 is the first light bulb is defective, E2 is the second light bulb is defective, are those independent? They are, but let's build up to that. So to answer this question, let's explore the probabilities of these 2 events. So what would be the probability of selecting a single defective light bulb? $500 over 10,000, which as a decimal is 105. So that's the probability of selecting a single defective light bulb. Now, let's say that one is defective. We go to pick a different one. What's the probability that the next one would be defective? To 4 decimal places.
Would it be the with replace or without replacement?
Without replacement.
So 499 divided by 9,900.
Yep.
How many decimals?
4. What'd y'all get? 0.04. No, 9.
Which means they're independent.
So these values are so close, and this yellow box is full of blanks. These values are so close to each other that when rounded to 3 decimal places, they're both 0.050. So for all practical purposes, we're going to treat them as independent. So this just reminded us that if a random sample of size n is taken from a population of size capital N, then the odds of selecting successive items from the population without replacement can be deemed as independent. The sample size at most 5% of the population. We already talked about that. This is just reminding us. So we'll ask the question again. What's the probability that both results are defective? Can we say our selection independent? Yes. So since we can assume independence, how would I solve this? Multiply what? 0.05, yes, but since they're independent, I go back to 0.05. Because they're independent. That makes sense. And Joe Credit, I have a little homework hint for you.
Wow.
That you may want a hint. You don't want a hint on the homework?
Oh,
I thought you said you had like extra homework for it.
No. I mean, I'll have to give y'all a hint. Friday. Okay. So let me ask y'all this. In AP, y'all can answer too if y'all figure it out. What's the complement of saying at least one event occurs?
Complement of at least one event.
What's that?
Everything else.
No events occur. The complement of at least one is none. So I just gave y'all essentially the answer to one question. So,
Mr. Schultz.
May I go ahead and go too?
just give me a
Okay. And then on That's right. That's right. Let me stop the recording while I'm talking that way.
Yeah.